Hello, and welcome to Lecture 2 of Magnetic Fields of Moving Charges in Phys 1204. We saw much earlier in the course that integrating an electric field over a closed surface, which we called a Gaussian surface, gave us a useful result, but we've also seen that doing the same thing for magnetic fields gives us a less useful result. Now we're going to see that integrating around closed paths, which we call Ampèrian paths, does give us a useful result for magnetic fields. So we've seen Gauss's law, we've seen two versions, one for electricity and one for magnetism, and we've seen how the one for electricity is useful for finding magnitudes of electric fields in cases of high symmetry. And we can understand it in terms of the fact that the number of field lines through any Gaussian surface is just proportional to the amount of charge enclosed in the Gaussian surface. On the other hand, with magnetic fields, where we don't have charge, we have poles, and they always come in pairs. The total enclosed poles is always an equal number of norths and souths for any Gaussian surface, and so that's why the flux is zero. But another way of understanding it is that every magnetic field line makes a loop, and so if a magnetic field line leaves a Gaussian surface, it must re-enter it somewhere else. And that's true not only for permanent magnets, but also for magnetic fields due to wires, because once again, the fields must make loops. So since surface integrals don't give us a useful result for magnetic fields, let's look at line integrals instead. And to keep contrasting electric fields with magnetic fields, I'm going to start off by looking at line integrals around closed paths for electric fields, and we'll see that we in fact get a familiar result that we've already seen before. So let's think about these two closed paths, 1 and 2, which go around this charge. And what are the line integrals of these E fields around these paths? If you think about it, you'll see that we already know the answer to this. However, it may take a little bit of careful thought to see it. Well, notice that for the circular path 1, wherever you look, the length element is perpendicular to the E field. And so we can see, since the E field is perpendicular to the direction we're going everywhere around the path, and there's a dot product in the integral, that integral must be 0. Well, what about the line integral around path 2? Well, notice that we can take path 2 and we can break it up into segments. We can make some segments that follow along circles and some other segments that go radially. And again, we know that on the circular segments, the E field is perpendicular to the direction we're going, and so those pieces of the line integral are 0 again. And so we can ignore those. On the radial segments, the E field is parallel to the direction we're going. And so we end up getting a simple integral of E dl. But notice that to come back to where we started, we have to go out as much as we go in, and that E field only depends on distance from the charge, and so all the outward pieces of the paths have to cancel all the inward pieces of the paths, and so once again we see that this line integral of the E field must be 0. Well, if you think back to things that we've seen earlier, this result is not at all surprising, because that line integral of the E field from some point A to some point B is just, other than a negative sign, the potential difference. And if we are starting and ending at the same place, the potential difference must be 0. So the line integral around a closed path of the electric field is always 0 for any closed path. And in fact, this is really just another way of writing Kirchhoff's loop law. And so we've seen that this always applies to any electric field, and any path we go around in it. And really, it's just a special case of the fact that the work done due to a conservative force around any closed path is always zero, since the E field integral that we're doing here is directly related to a work done. It's just a work done per unit charge. Well, enough about E fields. What we're actually interested in here is magnetic fields. So let's now think about these paths, 1 and 2, which are circles around a wire. And we know this wire produces a magnetic field, which is just a set of circles around it. So what are these path integrals? Well, notice that now, if you think about the direction we're going anywhere on one of these paths, we're always parallel to the magnetic field. And so the dot products are simple. They just end up being nice scalar multiplications. And anywhere around one of these circles, the B field magnitude is the same everywhere on the circle, and so that's a constant that pulls out of the integral. And so all we have to integrate is dl around the circle, and that's just going to give us the length of that path, or in other words, the circumference of the circle. So for path 1, if it has a radius r1, that gives us this expression. So we've got a nice simple expression for the line integral around path 1. What about the integral around path 2? Well, all the same arguments will apply, and so we're going to get exactly the same sort of expression. What we'd now really like to know is how to compare these two expressions. Well, it's reasonably easy to show experimentally that for a field due to a long wire, the B field's strength is proportional to 1 over your distance from the wire. And so in particular, that tells us that R1B1 has to be the same as R2B2, which tells us that the integrals around paths 1 and 2 are the same. And in fact, the line integral of the magnetic field around any circle centered on the wire must be the same. Well, what about paths that aren't circles? So I'm going to start off by looking at this path, and you'll notice that I've built this path out of circles. And so in particular, there's the one piece that I'll call arc 1, and it's basically like I took the small circle, snipped out this arc 2, replaced it with arc 1, and made some connections that are radial. Well, we know the line integrals along those radial sections are 0 because we're going perpendicular to the field there. And because the integrals around circles are all the same, we know that the integral along arc 1 must be the same as the integral along arc 2. And so the integral around this non-circular path is exactly the same as the integral around a circular path. Well, now, I can do that for any path. Once again, I can break this path up into segments that are on circles and segments that are radial. I know now that the integrals along the radial segments will all be 0, and all the ones along the circular segments will just add up to the same thing that I would get if I took any circular path around the current. Well, this gives us a qualitative statement of Ampere's law. It says that the line integral of the magnetic field around any closed path encircling a wire with a current in it is the same. And we'll write it this way, where what I mean by I enc is the current encircled by the path. And a closed path like this is called an Ampèrian path. What we mean by a closed path is any path, no matter what shape it is, as long as if you follow it around, you eventually come back to where you started. Notice that if I take a path that doesn't encircle the current, it would be something like this. So again, I can talk about an arc 1 and an arc 2. And I know that the magnitudes of the integrals along arc 1 and arc 2 must be the same, but notice that for this path, arc 2 is going opposite the direction of the field, and arc 1 is going with the direction of the field. And so those two integrals are going to cancel out. One is just the negative of the other. And so again, this integral is proportional to the encircled current, but now the encircled current is 0. Ampere's law, as we see, is going to play a role very similar to Gauss's law in electric fields. In other words, in situations of high symmetry, in particular things like infinitely long wires, Ampere's law gives us a very simple way of calculating the magnitudes of B fields.